Hello, my name is Dan Szumski. I'm an independent scholar. I live in Davis, California. The title of my presentation is Introduction to Theoretical Biology. The current paradigms in theoretical biology have proven woefully inadequate for understanding the fundamental processes that give rise to matter's living state. This is not a new realization. It has evolved over the past 50 years because life has stubbornly resisted all efforts to explain its basic principles. The grand vision of Crick, Delbruck, Elsasser, Monod, Waddington, and their colleagues has deteriorated to the point where only a handful of individuals pursue their mid-20th century vision of a triumphant theoretical biology, one which features the determinism and the precision that is worthy of being called a law of nature. Here's the problem in a nutshell. Life is an exquisitely organized form of matter. It exemplifies the very meaning of the words exact and precise. It performs along a timeline that is unidirectional but self-managed. It responds to changes in environment and nutrition almost effortlessly. It manages disease. It self-replicates. But no one can tell you how it works, and its secret continues to resist all scientific inquiry. In this lecture, I propose that it's time to re-examine the past century's observations, but from a completely different perspective. I'm not suggesting that we disregard or in any way minimize biology's remarkable data set, but I do think that we need to reassess the way that we assemble that data into an understanding of life's form and function. The current synthesis is simply not working. Our journey together will have some familiar landscape, but mostly it will be to places that few biologists have ever visited. In some instances, we will be altering the perspective from which we view the laws of physics, and in others, we will be relying upon entirely different laws of physics to explain life. In the end, you will see how all of life's diversity begins in two basic functions, synthesis and metabolism, and that each of these can be captured in a theoretical context that is completely deterministic, precise, and very exact. I'm only going to ask one thing of you. I want you to clear away what you think you know and put on new eyes, the new eyes of discovery. Then walk with me as we assemble a century and a half of physical theory and experimental biology into a new theory of life. You might be pleasantly surprised to see biology as it has never been seen before. Thomas Kuhn, in his eloquent dissertation, The Structure of Scientific Revolution, identified three types of phenomena about which new theory can be articulated. I want to draw your attention to the last of these because it alone characterizes biology. This third type are, quote, phenomena having anomalies whose characteristic feature is their stubborn refusal to be assimilated to existing paradigms. And Kuhn continues, this type of phenomena alone gives rise to new theory. That sounds like biology, doesn't it? Its characteristic feature is its stubborn refusal to be assimilated into existing paradigms. Thomas Kuhn is exactly right. We need to look at the cell from an entirely new perspective. Let me begin the discussion by taking a moment to summarize the goals of theoretical biology. In his wonderful book, What is Life?, Erwin Schrödinger coined the term negentropy to describe the cell's high degree of self-organization. This will be our starting point. We will describe the cell as a localized region of very far from equilibrium chemistry. Thus, our first goal. We want to understand how the cell's stable, far from equilibrium condition can be maintained, and we also want to know how it can be explained using the laws of physics. Second, we will consider our cell to be a localized region of a reversible thermodynamic process. This designation is not made lightly. Reversible processes are not supposed to exist in nature. Nevertheless, this designation alone is consistent with the cell's very far from equilibrium state, and for reasons that will soon become apparent, reversible thermodynamics is a far superior theoretical framework for understanding cell synthesis and function. Thus, our second goal. We want to understand the source of the energy that creates the reversible thermodynamic state and the mechanism that allows its temporal stability. Third, we need to arrive at a definition of free energy that is compatible with the degree of organization that we see in the cell. This will require a new theory of heat energy. So our third goal, we want to describe the differences in free energy storage in the inanimate world and in the living cell. Fourth, we see the vast amounts of heat stored in living cells, as for instance, when they are burned. We want to understand how this large amount of energy is stored in living cells that remain at room temperature. Fifth, biochemistry shows us how energy exchange continually takes place in the cell. There has to be some overall driving force that moves the cell's form and function forward in time. Thus, we want to identify and understand at the most fundamental level the forcing function that propels the cell's synthesis and metabolism forward in time. And sixth, the cell synthesis function is precise because it follows the DNA template. Metabolic function appears to be regulated with an equivalent precision, but with the ability to adapt to extraordinary range of environmental conditions. Thus, we want to know how the precision of the metabolic function is controlled with no apparent template. So how are we going to approach this modeling task? We know that it isn't practical to build a model of the cell's molecules. The number of variables is simply too large. However, there is an alternative that I have found useful in describing a manageable modeling framework. Earlier, we noted that the cell's molecular quantities represent a very, very far from equilibrium condition. It seems reasonable to assume that the energy structure that holds the molecules together might be equally as far from equilibrium. Here I'm not talking about the individual covalent bond energies, but rather the overall context within which molecular energy is stored. Energy has far fewer degrees of freedom than the molecular quantities. Energy can be described in terms of only a few variables. For instance, photon energy is completely described by either frequency or wavelength. With this background, let me briefly explain to you where we will be going. First, our theoretical framework will require one element of new physics. It is a new theory of heat that brings together into a single equation the two existing theories. We will require that this theory produces Planck's blackbody radiation results at thermal equilibrium, and that it then allows us to simulate the very far from equilibrium energy storage that will be required by our cell model. Secondly, in our quest for a theoretical framework, we will be going to the very limit of the second law of thermodynamics, as far from equilibrium as the laws of physics allow. We will be building our new cell theory on the physics of reversible thermodynamic processes. You are going to see how nature's most carefully guarded secret relies on the physics of reversible processes, and that is how nature has hidden its most coveted secret. I'll be guiding you through this new physics for the next 20 minutes. It's not as exciting as the biology that I will be discussing later, but it is essential that you understand these physics concepts if you are to understand the rest. so please just bear with me. Third, we will also need to revise our understanding of the respiratory enzyme carbonic anhydrase. In our model, it will be responsible for both gas and ion exchange at the cell membrane, all of which will take place in an active transport process. And finally, I will be proposing an obligatory influx of electrons across the cell membrane, which will serve to advance the cell's redox state, and with it, the entire cell cycle. I'll keep my descriptions as simple as possible, but I do need to explain some physics. For example, we will be analyzing Max Planck's theory of heat radiation. It describes how, at any temperature, billions of energy quanta are organized in a very specific form that is the same for all material objects at a particular temperature. Planck's results are generally summarized in a set of temperature curves that specify the number of energy quanta at each wavelength, or in our format, at each frequency. It is one of the most exact theories in physics. At any frequency or wavelength, it tells us how many light quanta are present and their total energy. But Planck's results are for an equilibrium circumstance that is inappropriate for our cell model, which is a very far from equilibrium state. So we will be dealing with a very far from equilibrium version of Planck's solution. And in this way, we will be constructing a new scaffold upon which we will be able to locate different kinds of molecules and even regions having a specific cell function. We will come to understand how the cell's energy is organized and also something about cell functions. Let's begin. A very generalized energy scaffold like this can serve as a framework upon which a model of the cell's form and function can be constructed. I want you to clearly see the most important element of this proposal, that is, its simplicity. It only involves 2 or 3 variables. Proton frequency and temperature are 2 of them. But even more important than its simplicity is the way in which it allows the theorist to look at the one half of cellular process that cannot be seen, the cell's energy structure. And because it cannot be seen, it can only be studied in its theory. Do you see how the existing biological paradigms, which place great emphasis on studying the molecules, is only one half of the cell's story? The other half is its energy structure. And there is no reason to believe that it is any less of a far from equilibrium condition than we see in the molecules. But instead of dealing with the cast of several million molecules, we only need to keep track of a few variables. After spending several years thinking about how energy might be organized in cells, I concluded that I needed to develop a very different theory of heat, one which includes non-equilibrium conditions, and more to the point, the very far from equilibrium energy storage that might exist within a living cell. So we will begin with some new physics, and to do this, we will initially concern ourselves with the photon's interaction with and absorption by an electron. I want you to consider a different way of viewing this interaction. It doesn't really change current understanding, but it does broaden our understanding in productive directions. We will consider the photon to be a reversible thermodynamic process. I want you to clearly understand what I mean when I refer to a reversible process. I'm insinuating perpetual motion. A photon in the vacuum of space is such a process. The photon process continues indefinitely without entropy production. It does so without fueling, even as it moves light years in the vacuum of space. Do you see how the photon satisfies the reversible process criteria? And because it is a process, it produces a work product, the transport of electromagnetic energy in space-time. Let me repeat that. The photon continues indefinitely without entropy production, without refueling, and it produces a work product, the transport of electromagnetic energy in space-time. Now let's return to our description of photon absorption and emission by an electron. In particular, absorption of a photon by an electron will require two steps. In the first, a one-dimensional photon is absorbed into the electron where it remains in its reversible thermodynamic state. It is only in the second absorption step that the photon evolves into the electron's three dimensions and enters the domain of irreversible thermodynamics. Next, I want you to consider a situation where the absorbed photon undergoes only the first step of photon absorption. It retains its reversible thermodynamic state, and it is immediately re-emitted, still in its reversible state. I want you to see that the photon has produced no entropy and lost no energy. It is unchanged during its absorption and during its emission. Finally, consider the possibility that the re-emitted photon is then absorbed by a second nearby electron, where it again undergoes only the first step of photon absorption and retains its reversible thermodynamic nature, only to be re-emitted, again in its reversible thermodynamic state, and then absorbed by the original photon, re-emitted, and absorbed by the second, and so on. We will take this perpetual movement between two electrons in very close proximity to represent the electrodynamic structure of a covalent bond. Do you see how it produces no entropy increase, conserves its energy, and can continue in perpetuity? Its reversible process work product is the union of two atoms, and in this description, the resonant photon's energy is conserved in a manner that can have an almost infinite number of values, these corresponding to an equally large number of energy states. Now, there are certainly other representations of the covalent bond that we could use, but this is the most straightforward for our purposes here. I want you to understand that we are specifically excluding Heitler and London's quantum mechanical description of the covalent bond. It is probabilistic, having Heisenberg uncertainty. In any reversible process space, which is after all where our cell model exists, everything is exactly deterministic, and descriptions of the photon absorption and emission can be explained precisely. Before we can go further, you need to understand some fundamentals of heat theory. The single best source of information on both heat theory and reversible thermodynamic processes is to be found in Planck's 1909 lectures at Columbia University. This is the starting point for the physics presented here. Heat energy exists in two very different domains. The first is what I will call the radiation domain. Its fundamentals were described in the frequency distribution of energy in Max Planck's equilibrium blackbody spectrum. The energy is stored in photons having a very precisely defined energy. Planck's theories is expressed as a single equation. It first introduced the quantum into physics, and it is one of the most precise theories in physics. The second theory of heat is more conceptual, but every bit as important to understanding energy storage. It is an earlier heat theory associated with the names of two giants of 19th century physics, James Clerk Maxwell and Ludwig Boltzmann. In it, heat energy is stored as molecular motion. It was Helmholtz's great contribution to physics, that radiant heat energy is always going over into random molecular motion, or in our theory's notation, mass domain heat. In these two theories, we begin to see the dual nature of heat. Radiant domain energy given off by, for instance, a radiator, and the heat of molecular motion or mass domain heat derived, for example, from friction. At a constant temperature, these two forms of heat energy are in equilibrium. I want you to consider that these two domains in which heat energy exists are completely separable. Heat in the radiation domain exists entirely as photons, while in the mass domain, heat energy exists as kinetic energy. You must also understand that heat energy is continually being transferred between these two domains, always in the direction of thermal equilibrium, where the mass domain temperature and the radiation domain temperature are equal. A simple thought experiment will make this clear. Consider two identical objects that we heat using two different heat sources. In the first case, we heat the object with radiant heat from the sun, and in the second case, we generate the heat from friction. We bring both objects to the same final temperature and then allow them to transition to thermal equilibrium. The mass domain and radiation domain temperatures will equilibrate, and it will not be possible to determine the method by which the initial heat was introduced. In this way, we see that heat energy is free to move in both directions between the mass and the radiation domains. I'm using this discussion to introduce a new theory of heat that brings into a single equation Planck's theory of heat and Maxwell-Boltzmann theory of molecular motion in an ideal gas. This new equation is distinguished in the way that it contains two temperatures, the radiation domain temperature, T sub r, and the mass domain temperature, T sub m. And at equilibrium, where the two temperatures are equal, this new theory produces Planck's blackbody radiation curves. However, and this is important, the elegance of the theory is seen in separating the mass and radiation temperatures in a very far from equilibrium way. We will be using this trick to simulate far from equilibrium energy storage in a living cell, something that we alluded to earlier. Now I want you to see how this far from equilibrium condition might occur. Consider an object initially at room temperature. We can raise its temperature with friction, and if we could eliminate the tendency of the system to move back toward equilibrium, this is what the spectral density would look like. The mass domain energy from friction makes the object very hot, and T sub m is called the thermodynamic temperature. Now watch what happens if we hold the mass temperature constant at, say, 300 degrees Kelvin, and raise the radiation temperature to 1000 degrees Kelvin. Again, we can eliminate the tendency for heat energy to move from the radiation to the mass domain to achieve its equilibrium, and the top of the new spectral curve lies along a straight line describing Raleigh's law at the thermodynamic temperature T sub m. However, both its internal temperature and its internal energy increase enormously. But, and this is important, it does so with no external indication of that stored energy. This is how energy will be stored in our cell model. Enormous amounts of energy storage in a room temperature device. The cell's energy will be stored in new covalent bonds, but the only way that we are going to see the radiation domain energy stored in these bonds is if we burn the cell. Otherwise, that energy cannot be detected. I want you to note, and again this is important, it is stored in a reversible thermodynamic process that produces no entropy, gives off no exhausts, not even light, and it produces a work product, the union of two covalently bound atoms. This is the energy scaffold upon which we will be building our model of the cell. The energy will be stored as redox energy, and T sub r will be an indicator of both the number of covalent bonds and also the total redox energy stored there. In this regard, our cell model will operate exclusively along a redox trajectory. I'll be coming back to this a little bit later on. I want to return to my description of the cell as a localized region of reversible thermodynamic space. We are now as far from equilibrium as the laws of physics allow. This places the cell at the very limit of the second law of thermodynamics, where entropy production ceases and where all thermodynamic processes are reversible. That is, there is no entropy production, energy is conserved, and a work product is produced. Now you may reflexively say, that's not possible. Processes that are thermodynamically reversible exhibit perpetual motion and are not supposed to occur in our irreversible world. The Clausius inequality is generally cited to describe the physical constraint. The change in entropy produced by any thermodynamic system operating at a temperature T must be greater than or equal to the change in the total heat energy of that system. This is typically taken to mean that the complete conversion of energy to work without entropy production is impossible. The reason is simple. All physical processes do, to some extent, result in friction or the conduction of heat energy, and this constitutes entropy production. However, the statement the complete conversion of energy to work without entropy production is impossible isn't quite correct. The Clausius inequality does not preclude the case where the change in entropy is identically equal to zero, but only the case where the change in entropy is negative. Thus, there is nothing wrong with operating at the limit of the second law of thermodynamics, where the entropy change is identically equal to zero. This is precisely the behavior that we saw first in the photon traveling in the vacuum of space, and second in the perpetual exchange of covalently bound photon energy. So what does this mean from a theoretical biology perspective? Well, most fundamentally, it requires that the amount of energy consumed in the reversible process space must always be identical to the amount produced within that space, at least during a process cycle. And the measure that we'll be using in that assessment is the change in Helmholtz free energy, which in all reversible processes must always be identically zero. I'm using the Helmholtz free energy in this context instead of the Gibbs free energy because the free energy measure in any reversible thermodynamics process needs to include all of the free energy in both the radiation domain and the mass domain. By contrast, the Gibbs free energy only includes the radiation domain energy. This is the reason that the Gibbs calculations break down in concentrated solutions. The number of mass particles is high, and therefore their kinetic energy cannot be ignored. Finally, I want you to know that in all reversible processes, there is only one outcome. From all of the possible paths that the process can evolve to, the one that does occur is the one that produces the smallest overall energy change. This is known as the principle of least action, and it determines exactly which of the possible next steps any reversible process can evolve to. Do you see how this makes all reversible processes exactly deterministic? Perhaps you can also see how important this is when we hope to model the precision of a living cell. One final comment on reversible processes. I want you to understand that our cell must be both exact and precise. Reversible thermodynamics is ideally suited to this purpose. Exact means that when molecules A and B combine to form C, we really mean that a specific molecule A and B combine to form a specific molecule C. There is no, quote, most probable concentration, end quote, of A, B, and C. There is exactly one molecule of C created from the other two molecules. Precise means the reactions occurring within the living cell's reversible thermodynamic space are always and everywhere deterministic. There is no Heisenberg uncertainty, and indeed no uncertainty of any kind. The probabilistic rules of quantum mechanics are incompatible with the reversible process. Likewise, the statistical mechanical rules that characterize aqueous chemistry are not appropriate here. Everything is exactly deterministic. The absence of this type of precision is entropy production, which is uncertainty, and uncertainty is not permitted in the physics of reversible processes.